Thank you. Thank you. Hello and welcome. Welcome to the Mike Lazaridis Theatre of Ideas here at Perimeter Institute for Theoretical Physics in Waterloo, Ontario, Canada. My name is Greg Dick. I'm the Director of Educational Outreach here at Perimeter, and it is a pleasure to welcome everyone here today to Perimeter's public lecture series. Both those of you here in the online, in the in-studio audience, and those of you watching online. Whether you're watching online on Perimeter's website or on one of our many science communication websites around the globe. Earlier this evening, we had Ontario's Education Minister, Liz Sandals, announce a special partnership which is going to allow Perimeter to amplify our student and teacher outreach. We will be able to reach more students in younger grades, train more teachers, and expand our reach into northern and remote areas of Ontario, including a traveling science exhibition. Please join me on behalf of Perimeter in thanking Minister Sandals. Thank you. Tonight's feature presentation will last approximately 1 hour and will be followed by a question and answer session. If you're watching online, you can participate by using hashtag #PILive. And we'll be following Dr. Kelly Foyle will be behind her keyboard with a team of PI researchers ready to engage in conversation and answer questions throughout the lecture. I will also take a question or two from the Twitter feed at the end. And again, that's hashtag #PILive to be involved in that online discussion. And now, we are honored to have with us the 2012 Nobel Laureate, Dr. David Wineland. Dr. Wineland's research as a member of the Time and Frequency Division of the National Institute of Standards and Technology led experiments showing precise control of atomic energy levels and motion. Through his research, he has been able to create incredibly precise clocks, which may allow the possibility of building a quantum computer. As a result of his research, Dr. Wineland was awarded the 2012 Nobel Prize in Physics for groundbreaking experimental methods that enabled measuring and manipulation of individual quantum systems. Tonight, Dr. Wineland will explore both the theoretical and the technological know-how that's required to make these ultra-precise timepieces. Please join me in welcoming to the stage, with his talk, Keeping Better Time, the Era of Optical Atomic Clocks, Nobel Laureate Dr. David Wineland. Thank you.
Well, thanks very much for the nice introduction, and it's a pleasure for me to be here. During the day, I've been finding about not only this program of speakers, but all the other outreach programs that the Institute sponsors. And anyway, I think it's really great what's going on here. Trying to explain what as scientists, what we find exciting, and trying to bring a bit of that to the public. So, okay, well, you can see the title here. So just to summarize what I'll try to explain to you, first of all, why do we need precise clocks? And I'll give you an idea how an atomic clock works, and if I do it right, within a minute, you should be able to go out and build your own atomic clock. So see how well I do on that. So I'm going to give some examples. Now, in our lab, we use charged atoms, and I'll mostly focus on examples from that, but neutral atoms are very good too, and there are strong competitors in trying to reach the highest accuracies. And I'll try to give an idea why single atoms are nice if we can work down to single atoms to make our clocks, and I'll give you an idea what the status of things is now and where we're going in the future. So throughout centuries, the main application of clocks has been in navigation. And I'm not a sailor, but what I'm going to say in the next two view graphs here will be very familiar to sailors. But the basic idea is that to find your location on Earth, the latitude, the position from north to south, is fairly straightforward. So for example, if you're on the Earth, on the surface of the Earth, and you can measure the distance, or pardon me, the angle between the level ground and the distance to the, say, the North Star, then this angle is a direct measure, can be directly related to where you are vertically on the Earth, the latitude. And the same basic idea applies to the longitude, but with one important difference, and that is that the Earth rotates. So the idea is the same, it's the same principle, but of course this angle is changing in time. And so in order to be able to relate this angle to where you are in terms of latitude, you need to know time. And to give you an idea, the kind of precisions that are involved, just with some simple math here, if there's an angle error in your measurement, that corresponds through the radius of the Earth to a certain distance error. And if we take, we can relate the angle to the frequency of rotation, one per day, and take the radius of the Earth. Then for an error of 1 second in time, that would correspond to an error of about half a mile on the surface of the Earth in terms of latitude. And of course, this is for sailors. You want precision's much better than that, of course, ideally. So that's. But anyway, this kind of sets the scale of the kind of precisions we're after. Well, and actually, there's some interesting history behind this. This shows how some governments can work sometime. Apparently, in the early 1700s, there was a series of disasters where ships were wrecked on rocks, and it was mainly because they didn't have precise navigation. So in 1714, the British Parliament sponsored what they called the Longitude Act, and basically they offered a prize of 20,000 pounds for a clockmaker who could make a clock precise enough, and the conditions then were that it had to be able to navigate over the period of months to an accuracy of about 30 nautical miles, and that corresponds to an error then over that time of about 120 seconds. And this, anyway, the most famous person working on John Harrison, he actually made a clock, and this is probably worth an hour's story. It's a very interesting story, but he was able to demonstrate. He made a clock. It looked like a big wristwatch, or a big pocket watch. But anyway, he had demonstrated this, and then the government said, well, maybe you should do it again, so we can check. And they kept pushing him off, and finally, after many years, the king intervened and said, well, we have to give him his award. And then I think, unfortunately, he died a couple years later. So anyway, getting back to science here. So these days, we know, of course, the way we navigate is with satellites. And the idea here is a little bit different, the basic feature is that if we can do very precise timing, then by some protocol we can find the distance, say, to a satellite. And the basic idea is that if we know the position of the satellite and we agree on some protocol to do timing, and it's much more complicated than this, but for example, let's suppose we have synchronized clocks, and we agree that the clock on board the satellite will send out a pulse of radiation, say, on every second tick. Then basically it takes there's a delay because of the finite speed of light, and so the signal received on the ground is later, and from that, but basically from that, the fact that there is this time delay, then you can determine the distance simply given by the speed of light times the time difference from when the signal was emitted and received. And to give you an idea of the error scales here, just some simple math here says that if we have a timing precision of a nanosecond, that corresponds to this expression to an uncertainty of about 30 centimeters. And so on board the satellites, we do now have atomic clocks, and if they have an error of, say, a nanosecond in 1 day, that corresponds to a frequency offset expressed fractionally of about a part in 10 to the 14. And so this roughly 30 centimeters is where GPS is these days. And so that gives you an idea, though, the precision of the clocks. We want the frequency to be constant, or at least known to 1 part in 10 to the 14. So that's the kind of scale we're interested in with our clocks, to be able to have frequencies that precise. And of course, it's a little bit more complicated than that. That just gives one dimension, but the system of satellites and GPS is basically allows you to over-determine things, and so you can do various checks amongst the satellites, and then by getting, because the satellites are arranged around a network, you can get 3-dimensional coordinates on the surface of the Earth. So what about clocks? And I think, most physicists, I think about time just the way everybody else does. It just kind of records the series of events. And I think there's some exotic theories that time may be quantized and so on. But for most of us, it's just as you would think of it. Just describes this progression of events. Well, for clocks now, what we want is something periodic. And so the basic idea of how we make clocks is we have some periodic event generator and then a counter, and from that we can easily get time. And the traditional periodic event generators we know are the rotation of the Earth, what I described before about the early navigation. And another example is pendulum clocks, which were sort of the clock maybe 100 up to 50 years ago. But now we have better clocks with the atomic clocks. So with atoms now, you can actually, the idea is not so much different than the pendulum clock. You can, in some cases, we have this picture in our mind that you can think of an electron going around a nucleus or passing through the nucleus, and so that latter case is where you can think of an electron going back and forth, but we know from quantum mechanics the electron gets kind of fuzzed out. But nevertheless, you can still think about an oscillation of charge about the nucleus of the atom. And so in that sense, the idea of an atomic clock is we just somehow have to be able to grab onto this oscillation to provide a reference for our frequency that we then can make a clock out of. So there's some, we know that we've learned that the frequency is given by an energy difference between two states, energy states in the atom, divided by Planck's constant. So it turns out that typically the way we don't measure often don't measure the oscillations directly, but there's another thing that goes hand in hand with this idea of an oscillation, and that is, if we start the atom in the lower energy state, and then if we apply radiation for a certain amount of time, and it'll be near, the radiation frequency will be in near resonance, we say almost oscillating at the same basic frequency as this atomic dipole, then basically then all we do is, if we started in the lower state, then we measure the probability of going to the upper energy state, and we know that when the probability of going up to the upper state is at its maximum value, then we know that the frequency of the oscillator we apply is equal to this natural oscillation frequency in the atom. So that's the name of the game. That's all we're trying to do here. So the way a clock works is not much more complicated than what I'll describe here. Is we might store atoms in some container, and actually certain clocks are made this way, where we actually might have a glass sill, and it's coated with material that allows the atoms to bounce around inside. But basically the idea is we'll send a radiation source through this sill, and when the radiation absorbed maximally, that's the same as the condition I mentioned on the last view graph, where that means the atom makes the transition from its lower to high energy state with maximum probability. And the way we tell it in this example is that we just look for the place where the absorption is highest, and then we can, the very simple electronic servo system allows us to control the frequency so that we reach this condition. And it actually is only slightly more complicated than that. If we were to only try to sit at the top of this curve, it's rounded at the top. So what that means is that if the frequency deviates a little bit, the amount of absorption doesn't change very much. So the only slight complication is what we do is we first go to, say, this side of the absorption feature, and then probe and measure the transition probability. And then we go to the other side. And basically then if we get to the condition where for those two probe frequencies where the absorption is the same, then we know that the mean frequency is equal to the center frequency, because this absorption feature is symmetric about its natural frequency. And that's it. We basically don't do anything more than that in these clock experiments. And of course, it's easy to write down a picture like that, but a lot of complications in between to realize it. And then, as I said before, the only last step is then to count oscillations of the oscillator that's providing this radiation to give us time. So why atomic clocks? Pendulum clocks are actually pretty good. The really good ones are amazingly good, even by quartz crystal standards. But so the pendulum clock, it basically, I won't go heavy on the physics here, but its frequency of oscillation depends on the length of the pendulum bob and also the gravitational acceleration at the location of the clock. And from this simple expression, which expresses the frequency of the pendulum, one of the things we have to worry about, there's a number of effects that we have to worry that might perturb the frequency of the pendulum. And one, for example, is one we have to worry about in general with our atoms too, is temperature. In the case of the pendulum clock, the dominant effect is where if the pendulum bob heats up, it tends to get, typically most materials get longer, and then that changes the frequency through the expression above. And to give you an idea of the sensitivity here, most metals will have a thermal expansion coefficient of about a few parts in 10 to the 6, about a few times 10 to minus 6 per degree centigrade. And a very good material might have one that's a couple of orders of magnitude smaller than that. But basically what that means from this simple expression is that the frequency change versus changes in temperature would be about almost a part in 10 to the 8th per degree C. Well, with atoms, we have to worry about temperature too. Now, typically with our atoms, they'll be at some temperature, and if the temperature changes, it'll cause a shift. And this one is interesting because it relies on one of the consequences of Einstein's theory of relativity, which says that if two different reference frames are moving relative to each other, then time moves slower for the one that's moving from where you're relative to where you're observing. And the interesting part about that is we know that our clocks run slower, but what Einstein, of course, taught us was something really profound. It isn't just the clocks run slower, time runs slower because of this so-called relativistic time dilation. Anyway, that is an effect we have to worry about. And to give you an idea, I won't go through the numbers here, but one of the traditional atoms to make frequency standards for many years is based on a certain transition, a certain oscillation in cesium atoms. And anyway, due to this time dilation shift, we can derive the temperature sensitivity, and it's given by this expression down here. So you can see it's dramatically less, this temperature sensitivity to temperature changes. And so that's one of the advantages. And this is just one effect that there's many effects we have to worry about that in controlling the frequency of the clocks. And this is one example of the things we have to calibrate for. So finally, the other thing is that, how reproducible are the clocks? And of course, in the case of the pendulum clocks, it certainly depends on manufacturing tolerances to try to hold the length of the pendulum bob to a very specific value. It also, from the same expression, it depends on the local value of acceleration of gravity, and that changes around the Earth. So that way, we have to take care of that effect. There's also the fact that, if you keep it running a long time, it'll, say, the bearing that supports the pendulum bob, it'll wear, and that'll cause the length to change. And so there's effects like that on a fine scale we have to worry about. Well, the nice thing about atoms is that, as far as we know, all atoms of a particular kind, say the Cesium-133 isotope, they're exactly identical. And so to the degree, then we're only limited by the degree how well we can measure those frequencies, but they're exactly identical, and atoms have the features they don't wear out. We can keep driving that transition forever, and it's never going to wear out. It's always going to be the same. So that's the big attraction of using atoms. So let me give you a little bit of history of how these transitions have been measured, at least the high precision ones. I showed you an example where we had atoms in a cell, and it turns out we can do much better, make more precise measurements with other methods. And so the case I'm going to describe is for the cesium atoms, and the reason I'll focus a little bit on cesium is basically since the mid-60s, the oscillation, so-called hyperfine oscillation in cesium, has defined the second. And in fact, the current definition of second continues to be based on this cesium oscillation, and so this particular transition frequency is 9 billion and so many cycles per second. And basically, when we make our clock, the way I described before, we just count 9 billion and so many cycles, and that defines 1 second. So now, this to give you an idea, the way these experiments have gone traditionally is that typically we have a system in vacuum, and we make a beam of cesium atoms that goes through a special, called a microwave cavity, but inside the ends of this structure here, that's where the radiation is applied. And rather than applying it continuously, it turns out, just for technical reasons, to be better to apply it in 2 places. But the key part of this operation of this clock is that we want this absorption feature to be as narrow as we can possibly make it. And it turns out that in these experiments, the narrowness of this absorption feature is given by, basically, it goes proportional to 1 over the time it takes to go through this apparatus. So when I first started working at NIST, which was then called the National Bureau of Standards, in the mid-70s, the idea was in order to make this feature as narrow as possible, we just made this atomic beam machine as long as we could. So in the apparatus at NBS at the time was almost 4 meters, and so the absorption feature, the width of this feature, was about 30 hertz out of this roughly 9 billion hertz, and that corresponded to a transit time of about 16 milliseconds that took the atoms to fly through this apparatus. Nowadays, the much more modern way is to realize this same kind of experiment is we use a technique called laser cooling, which I won't have time to really describe here. But basically, we know that lasers, you can think of it as photons that are directed along, and the photons carry momentum. And when they collide with something, including atoms, they impart their momentum to the atoms. And we can arrange the frequency of the laser beam such that when the atoms are going against the direction of the laser, the momentum exchange will then slow the velocity. And it turns out due to the first order Doppler shift effect, when the atoms are moving away, the absorption and the momentum transfer is greatly reduced. And so we get this kind of one-way effect where the atoms only feel this momentum, or dominantly feel this momentum transfer when the atoms are moving towards the laser. Anyway, using this radiation pressure kind of effect, we can cool the atoms down. And these days, now the way these kind of experiments work is that we're able to, with laser cooling, make a small blob of atoms that the temperature is on the order of a microkelvin or less. And then we can push again, using radiation pressure, we can push this blob of atoms up through a cavity, and rather than having two zones of this cavity, they go up and fall down. And so this is an example of this kind of fountain clock, we call it at NIST, and there's others around the world. And this tube where the atoms go up and down is about a meter long, which gives a time of about 1 second, which means this feature gets even narrower because of the long time between these two times of irradiation. So why optical clocks? And the answer is pretty simple. That is basically, if we can go to much higher frequency of oscillations than when we make our atomic clock, then and count the cycles of the radiation, then we can just divide any given unit of time, say the second, into finer and finer increments. So one of the experiments we started on quite a while ago now was to measure a certain transition, a certain oscillation in mercury ions. And this one now, rather than being 9 billion, it's about 1,000,000 trillion or 1,000,000 billion cycles per second, about 10 to the 15 cycles per second. So we get this huge win by going to high frequency. Now, we've known that for a very long time, but there's some things first of all, we had to make the oscillators that were very stable, in this case lasers, that could be able to take advantage of these very narrow absorption features, in this case about 2 hertz wide, on the order of the cesium clocks, but now at much higher frequency. And the other thing is we needed a way to count the oscillations, these million billion cycles per second. Anyway, is this a new idea? Well, no. In fact, one interesting thing, one of the guy at NBS wrote about a number of years ago now. He read through this text written by Thomson and Tate, and this idea was attributed to Maxwell, basically the father of electromagnetic radiation and so on. But anyway, his idea, as he states here, or as they state, they say recent discoveries indicate it's natural pieces of matter, such as hydrogen or sodium, which are all absolutely alike. That's what I was saying before. And they talk about maybe using a vibration of a sodium particle, and by that they meant these optical oscillations. And what's interesting in the second part of this statement here, they say it's it's known absolutely independent of its position in the universe. Well, they can be excused for not knowing about general relativity, but certainly they had the right idea that these ideas that all atoms would be the same, and these provided natural frequency references for precise time. So let me say a little bit more now about what our experiments are like. This one on mercury, the mercury ion. And in this case, we have this picture, this operational way of trying to realize the clock. We start the atom in the lower energy state. We apply radiation. In this case, it's in the ultraviolet, which can take the atom to this particular upper state. And this, of course, it again has a very narrow feature, just about 2 hertz wide, and such a high frequency that we get much higher fractional resolution. I won't describe much about the trap, but this what we call a trap, how we hold the ions, it's basically a very simple 3-electrode structure, and we apply a combination of electric and static electric oscillating and static fields to grab onto the charge of the ion and hold it in one place. And then we can irradiate it with this laser beam. Now, in fact, one little detail is that I mentioned, why do we want single atoms? In this case, it turns out that this upper state on the energy state on the mercury ion, it has a quadrupole, meaning that it's kind of shaped like electron clade's kind of shaped like a football, and it turns out that the electric fields from one ion, if we had just 2 ions in this trap, the electric fields from one ion acting on this football, this charged football, if the orientation is not preserved exactly, it can give really fairly large energy shifts corresponding to frequency shifts of about 1 kilohertz. And the name of the game for us is we want to get down to 1 millihertz, and it's very hard to control these shifts. So that gives you one idea why we want to go to just be able to use single ions. Now, in our experiments, we're going to detect in a little different way than what I described before. But the basic idea is that, again, we want to start the atom here, and we want to detect when it makes the transition with maximum probability. So in mercury, we also have another transition, and this one is we say allowed. It can scatter a lot of photons, and we don't need to know the frequency real precisely of this one, but this is going to serve 2 functions. First of all, it allows us to cool the ions down through this laser cooling effect, and typical temperatures are about 1,000th of a degree Kelvin absolute, and these days that's pretty hot temperature. A lot of the atomic experiments are down 1 million times lower in terms of temperature, but it's pretty good for our clock experiments. Anyway, we do this laser cooling to, again, suppress these time dilation effects that Einstein told us about. Actually, one thing here is we can, with a ultraviolet video camera, we can see our single ions. And in fact, one interesting feature of this picture here is that we have independent ways of describing or verifying how the size of the atom, that is the size of the wave packet that describes the atom, and it's about 500 times smaller than the spot size you see there, and the spot is just limited by the optics we have. So it's extremely well confined, much less than a wavelength of the radiation. So it's extremely bright compared to these surfaces here. It's just that the light is smeared out because of the limitations of the optics. Another side thing to say maybe is that most of the experiments we do on these atomic ions, the resonant wavelengths are in the ultraviolet, so you can't see it with your eye. But there's a couple of groups around the world that one of the ions that they use is barium, and it turns out barium has a transition that's in the blue. You can actually see an atom, a single ion, with your eye. It kind of looks like a faint star in these experiments. So again, coming back to the operation of the clock, we again, just to remind you, we're going to start the atom in the lower energy state, and then we apply radiation, and we want to find the case where it absorbs maximally. So what we do is we start the atom in the lower state, we apply the radiation, and then we turn the radiation off, and then we turn on this laser that we're using in part for our laser cooling. And it turns out if let's say the first laser, the clock laser, we would say, if it's not tuned correctly, it'll leave the atom in the ground state. And then when we turn on this laser, we see a lot of scattered light, and we can pick that up. On the other hand, if the atom makes the transition up to the excited state. Then when we turn on this detection and cooling laser, we don't see any scattered light. And in fact, the detection can be quite good. This shows a picture of a case where we left both sources on at the same time, and the atom jumps back and forth. So when we see scattered light, that meant the atom was in the lower state, and when there's very little scattered light, there's some background scattered light here, but that means the atom was promoted up there. But the key thing about this picture to note is that when we can easily set a discriminator in our detection so that we can tell with essentially 100% efficiency when the atom has made the transition. So some details, and there's many details. This describes a few features. It turned out in these mercury experiments for a number of years, the experiments were at room temperature. They're in a high vacuum, but not so high that one of the problems we had, it turns out when the ions are in this D state here, they have all this roughly 6 volts extra energy, and they're chemically very active. And the thing we found was if an ion in the upper state collided with a neutral mercury atom in the background, it was hard to pump it all away, that when they collided, it would make a dimer, kind of like a molecule, basically, and that killed our clock atom. And so, unfortunately, with the vacuums we could get at room temperature, this would happen about 10 minutes, which just was annoyingly short to get any useful clock operation. So basically, we decided to bite the bullet and go to very low temperature. And at liquid helium temperature, almost everything except there'll be some residual helium, but certainly it freezes out the mercury on the side of the container walls. And so we literally went from 10-minute times to 6 months, and the only reason 6 months was we did something stupid, electronically, and we lost the atoms. I mean, the vacuum gets incredibly good, and so we could get rid of that problem. It turns out by going to lower temperatures, we also we suppress various perturbations, including, we freeze out all the other atoms. So if at room temperature the atoms bump, or molecules bumping into the mercury, can cause some frequency shifts. And there's also another interesting factor you don't normally think about, but that it turns out just the thermal radiation in the room here, the electric fields are rather strong. They're about 10 volts per centimeter. They're, of course, in the infrared wavelengths, but the fields in just these thermal fields are surprisingly strong, and it turns out those can shift the frequency. But these effects, these so-called black body radiation effects, they go as temperature to the 4th power. So if we go from room temperature down to 4 Kelvin, we can really kill that effect. Anyway, so I mentioned before we needed, we had these basic ingredients, the atom, but we needed, first of all, to realize the full potential of these very narrow absorption features. We wanted a laser that its frequency would be even more stable, so we're not limited by the noise on the laser. So the basic idea of what we need to do, and all the clock experiments have to do the same thing. You want to stable, in this case for the optical transitions, you want to stabilize the laser so that its line width, in other words, its frequency fluctuations, are smaller than the absorption feature on the mercury. And the standard way to do that is you basically, all of us use 2 mirror cavities, and it turns out that the cavities, these electromagnetic cavities, they'll only transmit at certain discrete frequencies governed by the distance between the cavities. And the basic, for those that have a little physics background, basically what you want to do is you want to fit in half integral number of waves of the radiation you're trying to stabilize in between these mirrors. So if you can control the distance between the mirrors very precisely, then you can control the wavelength of the laser very precisely. And I haven't drawn, there's some simple servo system that allows us to realize that condition. Anyway, so Jim Berquist in our lab, who led this project, we had started on this project in 1981, and some years later, in a demonstration experiment, he and his guys built two separate cavities, so two separate stabilized laser systems, and then they could compare them, and they could show that the relative line width was much less than 1 hertz here, about 0.2 of a hertz, and that was then sufficient so that the noise on the laser didn't cause problems. We could realize the full potential of the mercury ion. And I always like a number of interesting things about these experiments. Since the laser frequency depends on the exact spacing of the mirrors, the big thing is you have to worry about is vibrations. And I was always interested that these, of course, you can see the way this, to cut down the vibrations, Jim took a very simple approach, was to suspend it on rubber bands, basically surgical tubing. And basically this provides a mechanical filter, but it turns out it worked very well. And they could get these results. One of the interesting things, though, is when the cavities, for tuning up all the optics on this small optical table, when they're sitting on the when it's sitting on the ground, you can see, of course, a lot of room noise and so on. But there's a characteristic kind of a broad smear of noise at a less than 1 hertz, about 1/7 of a hertz, and this noise is actually from the waves crashing on the beach in California, about 1,000 miles away. So it's just amazing the sensitivity of. And for those that know a little bit about this is the basic idea of the gravitational wave detectors: is to look at the strains of space-time induced by gravity waves by looking at the change in position between two mirrors. Well, there was one other ingredient. So even if we could make now this laser that was very stable to be able to take full advantage of these very narrow absorption features of the ion in our case, there was one other ingredient was measured. How do you measure these billion cycles a second? And I won't. It's not real complicated, but I think a lot of people aren't physicists out here, so I'm not going to go through the explanation here, except to say that we can make an arrangement where if we have what's commonly called mode lock laser, and what you can think about here is that we have a continuous wave that's coming out of our laser, but its amplitude is modulated in a way such that these at the times when it's actually we're seeing radiation is very short time compared to a time of oscillation of the compared to the period of oscillation of the central frequency of the ion of the laser. And it turns out if we can lock the position of the optical waves to the position, the time of this envelope that describes the amplitude modulation, then we have a simple way to do that, but I won't go through the details except to say that when that condition is met, when these waves don't slip underneath this envelope, then it turns out that these pulses that are coming out, described by these amplitude modulation envelopes, it's exactly related by an integer to the oscillations of the optical waves underneath. So we don't directly, by this method, we don't directly count the oscillations of the optical oscillations, but because of this, knowing this exact ratio, and by other means it's easy to determine the integer that we have, then we can relate the optical frequency to the rate of the pulses coming out. And the rate of the pulses coming out for typical setups are maybe on the order of 100 megahertz to a few gigahertz, and it turns out we can actually easily count the pulse rate of these lasers coming out. And this was a really important development. It happened actually over a relatively short time, and Ted Hench and Jan Hall, inventors and their colleagues, the ones that really invented this technique, were they won the Nobel Prize a few years ago, in part based on this invention. So now we have what we need. We have a way to make narrow radiation to probe the resonances, and then a way to effectively count the oscillation periods. And so, as I mentioned Jim Berquist. He was the one in our lab that headed up this experiment. Now, a couple of the features: the fact that we hold the atoms in one place. They still may be jiggling around a little bit, but the fact that on average their velocity is 0 means that the first order Doppler effect, the effect you know about when say a fast motorcycle goes by you, and the pitch is high when it's coming toward you, and it's reduced when it's going away. That's due to the first order Doppler shift. The fact that the velocity atoms on average goes to 0, that takes that shift away. Now this laser cooling reduces the relativistic time dilation, and I've already mentioned some of the features of going to low temperature, and there's a number of other things we think about in this. But anyway, in these experiments, we had been working on this since 1981, but finally in the mid-2000s, we finally got to a place where the inaccuracy due to all these effects, including the couple of the ones I mentioned there, were small enough that we were actually doing better than the cesium clock. Of course, over the years, cesium always was getting better, so it was kind of a moving target, but we finally got to that point. And in some ways, this is you might say this was kind of the start of the era where we're now all going to these optical transitions to make clocks. Now, there's a number of other ions that are interesting, and there's even a transition, a nuclear transition, which of course most nuclear transitions are very high energy, gamma rays and so on. But there's it looks like in thorium there might be a transition in the visible that we could use these same basic ideas on. And for the physicists out there, there's a nice recent review on these optical clocks that you could look at. So I'm going to say a little bit here now at the end about, we're using some ideas. Actually, I have colleagues here at the Perimeter Institute, and one of the focuses at Perimeter and also at the university here is quantum information. And we've been able to use some simple ideas of quantum information, quantum computing, in our clock experiments. And so this project, which in our group is led by Till Rosenbaum and Dave Leibrant, it turns out that we've been kind of eyeballing aluminum ions, and one of the reasons is it has a much longer lifetime in the excited state than mercury, and such that the absorption features are even much narrower than mercury. So we wanted to take advantage of that. In principle, we could detect, just as I described for the mercury experiment, there's another transition where we can scatter lots of photons, and we can see which, by this state-dependent scattering, we could tell which of the clock states the atom is in. Unfortunately for aluminum, this is at such a short wavelength that we just don't have any lasers that work there. And so what we're doing is taking some simple ideas from the quantum computing related experiments. And in this case, what we do is we put our aluminum clock ion and we put it in the same potential well along with a magnesium ion. And you can think of this at the low temperatures we operate at with laser cooling. It's kind of like you can think of this as kind of like an artificial or pseudo molecule. It's like a diatomic molecule. Anyway, this pseudo molecule, it has certain characteristic vibrations. And anyway, what we can do in this experiment, again, the protocol is the same. We're going to start the atom in the ground state. We apply radiation, and then we want to see whether the atom has made the transition. Well, it turns out with using some of the basic ideas that we employ in these quantum computing, quantum information experiments. What we can do is we can map the quantum states of the aluminum ion first onto the quantum states of motion of this pseudomolecule, and then we can map those quantum states onto, in this case, magnesium. And it turns out magnesium, we can use this trick. The wavelength is much more manageable. So indirectly, we detect the state of the aluminum ion by mapping onto the magnesium ion, which we can easily detect. And so there's some other additional advantages of doing this. So for example, again, coming back to the time dilation shift, it turns out that for the length of time we can probe this atom, during that time there's noisy electric fields in the background which can heat it up and cause problems with a shift due to the time dilation shift. And but anyway, it turns out these wavelengths that affect the magnesium are substantially different than those that affect the aluminum ion. So we can basically keep this laser cooling on continuously while we're probing the aluminum ion to suppress these time dilation shifts. There's some other features that I won't go into here, but anyway, basically, so with this aluminum clock, we've been able to do somewhat better than the mercury for a number of technical reasons, and some other groups are picking up on this method too. So let me say a little bit again about these frequency shifts. Some of the most interesting ones are again the Doppler shifts. So I mentioned just a few slides ago I mentioned that basically the fact that the atoms are held on average in one place, that means that this expression here for the first order Doppler shift, it averages to 0. And I've described this as the time dilation shift, so-called second order Doppler shift. Now I lied a little bit because what I said, even though the atom in the trap its average velocity is going to 0, it's relative to the trap. And the problem we have is that basically the laser is on one end of this optical table, and the trap is on the other end. Well, the temperature in the room changes, and that causes the table shrinks and contract, and that causes a first order Doppler shift we have to worry about. And the kind of sensitivity we need to worry about is a shift of velocity between the source and the absorber that is only 0.3 of a nanometer per second, and that can be caused by these temperature changes in the lab. So we have to take care of that. And actually, what we first got the idea from satellite ranging, the way one technique for measuring the range distance of satellites from us, or more commonly in deep space probes, is that they basically measure the first order Doppler shift by essentially reflecting a signal off the satellite. And then you just integrate that effect, in other words, the velocity, to get the distance. Well, we use the same basic technique as that to take out this small, very small but important velocity. Is we take a sample laser beam from where the clock laser is, and we reflect it off the trap and then bring it back, and we can measure this shift and account for it. So anyway, a couple of years or so ago, with all these, taking account of all these systematic and environmental effects, we got down to an inaccuracy of a little under a part in 10 to the 17. Now, there's one other shift we have to worry about, and it's also due to Einstein. And in addition to the time dilation effect, or this is another kind of a second version of the time dilation shift. The first one is due to the relative movement of reference frames, and the second one Einstein told us about is that clocks run at different rates and different gravitational potentials. And it's an effect we're now starting to have to think about. And it's a small effect. To give you one example, a human example, is that suppose you had a twin sibling and you were separated at birth, and let's suppose you moved to Boulder, Colorado, and you lived there for your lifespan, let's say 80 years. And compared to your sibling after this after this 80 years, due to this gravitational redshift, it turns out you'd only be about a millisecond older than your twin sibling. So it's nothing to worry about on a human scale. On the other hand, it's an effect we have to worry about with our clocks. And so to kind of illustrate this effect, we did a kind of a cheesy experiment. It was fun to do. And that was the following, is that basically this was one of our aluminum clocks. You can see it's not ready to wear on your wrist yet, and we had an identical one in an adjacent room, which is not shown here. But anyway, these two clocks were basically at the same height in the labs, and we could measure the frequency ratio of these two clocks, and it was basically unity with some small error here below a part in 10 to the 17. And then what we did is our postdoc at the time, James Chow, as you can see, he's put some jacks underneath the table here. So he raises the table up here and about 33 centimeters, and then compare the frequency of the clocks. And it's not a strong effect, but it's statistically significant that we could see this frequency shift due to the gravitational potential redshift. And this is an effect we have to worry about. Actually, one thing that was to me, it was kind of disappointing in a way, because it turns out that we have to account for this shift, and there's other ways to measure the gravitational potential at various locations. For example, you can take devices that measure little g and do it at various places in between where two clocks are separated. And from those measurements, you could determine the gravitational potential difference. But due to uncertainties in that process, you can only know, say in Boulder, Colorado, where we can only know the gravitational potential redshift to about 3 parts in 10 to the 17, which corresponds to roughly this height difference. So as our clocks now are more accurate than this effect due to the gravitational potential redshift, and what that means is the only way we can compare two clocks precisely is that they have to be in the same location because of this effect. And like I say, I didn't say, but I started my graduate school working on atomic clocks and did various things in between, but I always returned to clocks, and it made me kind of sad, because in the end all we have is a kind of a crude altimeter based through this gravitational redshift. Well, you have to take the high road, and now we say, well, we're going to help the geodesists map the gravitational potential around the world, the so-called geoid. And anyway, so how are we doing? And it turns out for several years we kind of held the record on precisions, but in the last year or so there's been 3 other experiments where the precision has improved. We were at about 8 parts in 10 to the 18, and even this one here from our colleagues down the street from us at the University of Colorado, they've got down to this level here. They hold the record right now. So we still have our work to do to kind of get back in the game here. So what about the future? I think certainly with GPS we can usually find the store we want to go to, and you might say, well, do we need anything better? And it turns out through centuries, whenever there's been a better clock, there's been a use for it. And one thing we kind of look for, one possibility is it's again navigation, but suppose we could navigate down to less than the centimeter scale. One thing that's observed is that a precursor of earthquakes is strains in the earth. That is, where, say, different locations separated by on the order of kilometers, they go through relative height changes, which is this strain, which is then an indicator or precursor of earthquakes. So if we can get down to that level, we might have a way to help in earthquake prediction through these strain measurements. I mentioned this idea of mapping the Earth's gravitational potential through the redshift. I think as scientists, those are great applications, and wonderful we can contribute in that way. There's always, we're always interested in testing the, theory, and particularly Einstein's theory of relativity. So far, he's survived just fine, but maybe at some point, maybe we'll find, for example, maybe we'll find a deviation from his prediction of this gravitational potential redshift. Doesn't mean he's wrong, but maybe if that happens, maybe there's some new physics that we're uncovering. And so we're always trying to push the boundaries, the accuracies of these tests of both Einstein's theory. Another thing that's kind of been popular is that, in principle, at least nobody knows that it couldn't be true that the relative strengths of the fundamental forces, say the electromagnetic forces and the nuclear forces, the ratio of the strengths might be changing in time, and there's people that postulate that. And so one of the things we've been able to do is to, by comparing the frequencies of clocks based on different atoms, which means different mixtures of the strengths of the fundamental forces, we just measure them in time over years, and we can start now to put pretty strict limits on how much they could be changing. So anyway, there's a lot of interesting, besides just the clock applications that we can think about. Finally, let me just conclude by saying, of course, this is a project of many people. This shows our group from about a year ago, and certainly all the work is done by the many students and postdocs and visitors and my other fellow staff members. And so, and let me also say there's a number of groups around the world working on this same problem. So it's a pretty big enterprise. And anyway, with that, I'll stop. Thank you.
That was excellent. Thank you. Yeah, you can go to center stage and all that. Thank you very much. Okay, we'll open the floor to questions, both in studio and online. Maybe we'll take an in studio question to start. Go ahead.
Okay, I gather that there's a big difference between building an atomic clock in the lab and building one that can be put inside of a GPS satellite. So, what's the gap right now between what you can do in a lab and what's possible to put in a satellite?
Well, I mean, in terms of timescales, it's probably on the order of a couple decades. That is where you can shrink things down to be able to put in a satellite. So the atomic clocks on board the satellites now were basically the state of the art about 20 to 30 years ago. And they've, with the engineering developments over the years, they can make them very compact. And I think, it would be natural in this case too. Those tables of lasers you saw obviously aren't ready for the satellite, but we certainly see our way towards making very compact systems. So I think it's just a natural progression. I mean, there'll be certain cases where we can't shrink it down, but I think the general trend is there. So we'll continue to see more and more accurate clocks on board the satellites. I think it's pretty clear. Yeah.
Okay, let's take a question from the online Twitter feed from @DaveFish. Doesn't Heisenberg uncertainty principle cause problems with holding the mercury ion still?
Sorry, I just missed it.
So the question is, does the Heisenberg uncertainty principle cause problems when you're trying to hold the atom still?
No, that's a good question. In fact, I mentioned when I showed the picture that the size of the atom was about 500 times smaller than the image we saw. Yeah. And in fact, the size is limited by the uncertainty principle. That is, we know from Heisenberg that if we try to position a particle too strongly, its momentum and then therefore its kinetic energy gets larger and it spreads out. So the case that we talked about, it's sort of the kind of states we realize where the atoms are sort of the optimum, where the spread due to the uncertainty and the momentum and position are kind of balanced out to be the optimum case. But the question is a good one because we can't confine it to a point. We're limited to a certain size of this. We talk about the wave packet size, and that's a direct reflection of the Heisenberg uncertainty principle.
Thank you. Let's go in studio.
first one, this is like I have two questions. First one is, why are all of the kinds of atoms that you talked about using in the atomic clocks in this lecture are metals?
Oh, I think there's nothing, in principle, there's nothing, that's a good question. There's nothing magic about metals. It turns out, though, that at least directly, indirectly, there is a correlation, because what we want to have is certain kinds of energy states, certain properties of the electrons, and in many cases, the desirable properties of the electron configurations that make good clocks also turn out to be metals, but it doesn't have to be a metal.
Okay. And my second question, so why, if you had an atom that would have sort of like two different like patterns, like had like a sort of kind of light emission or something like that, and it also vibrated, couldn't you use the like both of them, like so that you could make it more precise by doing like the pattern of one, like from getting a signal from one to the other and then the other one?
I see. Well, maybe I'm not quite understanding your question. I've talked about the fact that we want to use single atoms in these experiments. I talked about how one atom could perturb the other in the mercury example. But one way to answer your question is certainly we would like to do this on more atoms at once, because we just get more signal that way. So that's a very good point. Now, about them talking to each other.
I didn't mean it like that.
Oh, okay.
Like one atom that was like, so that it wasn't in the middle, like so it's forced to vibrate between like an area, and so you could do the middle, like, and it also has a like sort of like a light emission, something like that. So you could do like one signal to the other signal, and then you could get a smaller reading. If they're on similar scales.
It's pretty complicated scheme you got there. Maybe we can talk about it a little later.
Yeah,
okay?
maybe that's
anyway.
maybe for a longer discussion, but that's a great question. Thank you. We'll go online for a question. Thank you.
Thank you.
I have an online question here, which, because perimeter is so involved in gravity wave detection, the question essentially is asking, how will the clocks and very precise clocks impact the search for gravity waves, or will it?
Well, I think it's just a little out of my realm, I would say. But certainly one thing that people talk about is if you had, at very large distance, say if you could have clocks in outer space, and you would, one way to sense gravity waves would be to look at the relative perturbations on the clocks. So this is a little different than the interferometer experiments. I described how we stabilize lasers to a cavity, where you look for vibrations there. So it's a little different approach, but I think, people think about those experiments where you have widely separated clocks, and you would look for distortions in space-time through by comparing the frequencies. So, it's a possibility. It's not there yet, but certainly a lot of people think about that.
And let's take one last question here from in studio.
Hello. So you mentioned there's various atoms that you can use for the atomic clocks, and the frequencies for each atom, element, is different. So is there a trend that's seen on how different they are between the elements, and could you use a possible trend to predict the frequency of elements that haven't been used?
Well, in general, no. I think, if I understand your question, I think in general, no. And the reason is that the effects that go into actually determining the frequency, first of all, it's a many body problem, typically with many electrons around the nucleus, and these effects are so complicated that it's hard to predict. For example, just one thing I can say, the theory of that predicts the frequency of the aluminum transition, or the mercury transition for that matter, is, gives a prediction that is in terms of accuracy, many orders of magnitude less than what we can measure. So it doesn't really, in that sense, the theory can help us predict roughly where the frequency is, but by trying to extrapolate between different species to predict the frequency of another, it's at this level of accuracy, it just doesn't work. So, yeah.
Thank you.
Yeah.
Ladies and gentlemen, 2012 Nobel Laureate in Physics, Dr. David Wineland.
Okay.